Okay, everybody, we're going to be getting started in here in like 2 or 3 minutes, so if you could start making your way. Before we start, Eli, why is it kind of delayed? Okay, we don't know why it's kind of delayed, but I'm just going to keep talking. 2 small requests before we start. When you guys are getting situated, 1, if possible, please do not stand in front of the live stream camera. And then 2, please stay clear of the big red carpet down the center. That's where the Rover is going to drive. Other than that, please find a seat, sitting, standing. Much appreciated. We'll get started here in a few minutes.
we there? Okay. Whoa. Okay. So on the mechanical sub-team, we go through a 1-year design cycle, designing and then manufacturing and later testing. On our system, we have our robotic arm, our mechanical science system, our autonomy head, our drone, and then the rover body itself, the drivetrain. Within that team, we have leads of each of those, and then a group of members who serve under that. As we go through the year, we begin with our design cycle. We teach members their trainings in both CAD capabilities and then element analysis beyond that. After that, we go into the early design review process, where we actually check every system. We give freshmen projects, and we allow them to learn and build on their own knowledge. And then once we finish our review process, we go into manufacturing. That goes from our in-house machine shop, where we do metal components, to composite fabrication and 3D printing. And then once we do that, we go into the point you see now, where we have a working rover and we test, and we get to show it off to a lovely group of people like you guys. And then apart from that, we go to competition with our system. But that is an overview of mechanicals.
Hello. Okay. I'm Garrett McIntyre. I'm the team's electrical architect, so I'm in charge of all the electronics on the team. Just like mechanicals, we have leads under each of the systems. So we have a core lead, a arm lead, a science lead, and we also have a science lead. As far as what we do, we go through the entire design process every year as well. We start at the beginning of the year, coming up with requirements for all of the circuit boards that need to go on the rover. And then we teach all of the members how to go through the CAD process, how to design the circuit boards, how to create the CADs. Then we order all those, take them through the manufacturing process, teach them how to solder these boards, so that way we can get finished circuit boards. And then at the same time, going in parallel, also teaching them how to write embedded software for these boards, and going through the software writing and review process as well. And then taking those two parts, the hardware and the software, putting them together into a complete package, and doing the validation testing on that, so that way we can get, working stuff on the rover. Because as nice as the mechanical stuff is, it does not actually do anything without the electronics to actually drive it. So that's kind of our big job, is making sure everything actually works. Yep. So that's what we do. Getting you the working rover that will be driving out here in just a little bit. And then, for the rest of the year, going through the revision process, trying to make all the software and hardware better as well.
Okay. I'm Morgan. I'm the base station sub-team lead here on software. As you might have guessed from our team name, essentially we do everything relating to software. That includes, for example, our autonomy code base, which ensures the rover is able to autonomously drive with no user input, which involves both computer vision algorithms and navigation algorithms to ensure it's kind of reliable and safe during our autonomy task. And to go along with that, we also have our simulator we've been working on this year, written in the Unreal Engine 5, where we take map data from Utah, where we compete, to make a simulator that's as realistic as possible, so we can test idealistic conditions for driving the rover and testing autonomy. And finally, we also have our base station, which is our custom UI software that essentially encapsulates all the different systems on the rover and lets drivers actually control them effectively. So from the beginning of the year to the end of the year, we're very focused on making sure new members get experience on essentially every design step of the design process. And we're also committed to making sure what we do on the team is very much what you would see in a real world software job. from the first steps of like designing a feature, going all the way to the end, doing code reviews and final changes.
Hi guys, I'm Sophia Tripp. I am the science discipline head. So the science sub-team is a little different than the rest of the sub-teams because it incorporates a lot from every sub-team, the mechanicals, electricals, software, but then we add our own little spin to it, which is the science portion. So at the beginning of the year, the members come together and we all distribute projects, and they do heavy research into what exactly they're doing, why we're doing it, what chemicals we're really looking for, and then we go into actually developing the optical layouts for those custom-made instruments to analyze signs of biomolecules in soil samples. So this year we have a custom Raman spectrometer and a custom autofluorescence microscope that's going to look at the subsurface sample. But yeah, they're incredibly hardworking. Later this year, we're starting to get into actually understanding what the judges are looking for in terms of presentations, really nailing down like.
In charge of all of our social media and any public events we run. This one, or if you follow us on social media, last semester you saw we ran the Tour of the Planets event and all of our other Space Week events. And so we're in charge of planning all of that and making sure people see our team and what we do, and make sure people know that we're having a good time over here. So yeah, that's what the PR sub-team does. And now
Okay, thank you all of you for summarizing what your sub-team does. Again, after this main Rover portion, after we reveal our Rover, you can walk around to these stations, hear more about what your students work on. Hopefully they all just go and show you on the systems, I made this part, I wrote this code. That's really the cool aspect, is finally seeing the fruits of all your labors at an event like this. So, okay, next up, we are very privileged today to have Jack Tuschmidt, an alumni of our team, here to speak further on the team's mission and wide-reaching impact. Jack was a member of MRDT from 2017 to 2021. He spent time on the team as a mechanical lead and was the 2019-2020 MRDT CEO. He also held the peer mentor position at the Student Design Center in 2020 and 2021. Please join me in welcoming Jack.
Testing. Oh, there we go. All right. How's everybody doing today? Awesome. Thank you so much for having me, Abby. It's really a pleasure. I want to talk a little bit today about what it is to be an alumni of this amazing team, and what it is to be an engineer in general. A sequence of controlled failure. In 2022, I became an alumni. I was organized. I was really excited to make change. And honestly, I was ready to apply what I've been learning. In 2017, on the other hand, I was a freshman. I was disorganized. I was all over the place. And honestly, I was like a kid in a candy store who wanted to do everything, everywhere, all at once. I would really try and coerce anybody that was around me into legitimately doing any campus activity, and I would bail on them at the last second almost every time. I think it was the first day of O week when I turned to my roommate at the time, and also my best friend, maybe my only friend, and said, "We got to join a design team." And so we signed up for the first onboarding meeting for Rover. Naturally, Eli spent the entirety of the first semester on Rover alone. I bailed on him last minute. I didn't show up. This first semester where I wasn't on Rover, honestly, this was the semester that gave me the most perspective as to what design teams in general bring to the table for the student experience here. See, I was really caught up in this idea of prioritization. First, you prioritize your grades, then your part-time job to get a little cash on the side. Maybe you go find an internship while you're at it. And then if there's some time left over, maybe some fun. But for the most part, no fun. My friend, on the other hand, he was going about it in an entirely different way. You see, Rover was fueling his technical passions, but it was also his fun. And it became this backbone of his classroom education, directing his questions and attentions to what mattered most. To put it simply, while I was getting burnt out, he was getting excited. So by the end of the first semester, I knew I had to check Rover out. Now, I joined the first all-team meeting, and I got assigned to the Rove Core Mechanical subteam. That's when I was given my first project. See if this will go. This was in 2018 during Atlas year. And Matt was my mechanical team lead, and he said, very simply, design something to hold a circuit board. It was a really low bar. So for 2 straight days, with no sleep, locked in, grinding away at the computer, I was going to present Matt, my team lead, with the sleekest, most intricate, thought-through modular circuit board design that you could possibly imagine. It was this puzzle piece right here. Here's the rub, though. When this puzzle piece had the near super glue-like adhesive Velcro stuck to the bottom and then interlinked with all of the other puzzle pieces on the Rover, you could almost lift the entire Rover up by it. Modular was not an option. You weren't getting this thing off. I think it was a week that went by before Matt ended up scraping all of these off with a putty knife. And it probably till this day goes down as one of the worst designs to ever make it on the Rover. It was the first in a sequence of controlled failure. So at the beginning of next year, it really came as a surprise to me when they decided to pair me up with a freshman by the name of Remy. I might be showing my age on that one, guys. Now, the interesting part was that they wanted us to design one of the most complex parts on the Rover this year. And it was for a brand new suspension design called Widow. Here's Widow. Here's us talking about it. Now, perhaps our design was maybe slightly better incrementally, but honestly, that in a combination with some other factors, it was still so rough around the edges that leadership on the team at that point made a very wise decision to take a hard fork from the design and stop the development of the new suspension altogether. Once again, I was up with very little sleep, redesigning pieces from the previous year's suspension locked in at the computer. But this time I had some friends to help. The manufacturing delays, they actually ultimately led to a significant lack of testing. And that resulted in, ultimately, the catastrophic failure in competition. It took us from potential top 3 down to 5. It was another moment in a sequence of controlled failure. So at the end of that year, it came as a big surprise when the team thought it wise to elect me as CEO. I think by that point, though, I'd really gotten the point of it all. See, Rover will always present the students with mishaps and mistakes. But by doing so in a controlled environment, initiating a push for improvement, that's what differentiates the Rover members from the rest of the student body here on campus. See, our students on Rover, they have a genuine passion to work tirelessly. And they're motivated to struggle, especially by the fact that they know that their peers are really counting on their success. And I honestly think that's really what contributes most to the fact that students on Rover consistently graduate with higher grades, at higher rates, and with better job placement than pretty much any other campus organization. It's also marked by what our Rover members are doing in industry today. You see that Apple Watch on your wrist, or the satellite flying over your heads right now? Maybe that rocket launch you were inspired by last year. I'm going to keep going. The AI in our pockets, the cell phone towers above us, your home computer, and the electricity that runs through it, plus the defense systems that keep us safe. All of those have Rover alumni tackling the most difficult challenges. It's not hard to see how big and deep this team goes. At this point, I really do want to drive this point home though. So I want to show you guys a few images of what industry expectations are right next to what we see on Rover. Here's some CAD design. Here's some finite element analysis, some manufacturing and machining, and some circuit board design. Just in those pictures alone, it's not hard to understand why there are alumni that are coveted at all of these different amazing companies. So with that being said, today I really got a favor to ask everybody here. First, when you get a chance to take a look at this year's Rover here in a few minutes, I want you to take a second and really take it in. And I really want you guys to push yourselves to ask yourselves the difficult questions. What were the struggles and the mistakes and the mishaps that these students had to go through to persevere and bring this thing to life? Because that's where the heart and the story of every year's Rover resides. It's in those controlled failures that these students have grinded away in order to make this year's Rover the best yet. Next, when you're on your way home tonight, or when you're about to go to sleep, or even maybe on your way to work tomorrow, I want you to take a step back and pause in your life at some point. And I really want you to think and realize that what you're seeing here today, what you're actually watching happen, what's happening here today, it will directly have an impact on the education of these students tomorrow. And undeniably, that will impact how technology shapes our worlds for the future. Thanks so much, Abby, for having me. Let's get back to you and get me off the stage.
Mike. Oh, we're back. Okay. Thank you again, Jack. And now moving on, transitioning into what we've been anticipating during this entire event, what our big day is. Let me click over here to the next slide. So if we could get our operators moving up here. Here they come. Okay. So the culmination kind of this event, of our work this year, of why we're all are here and what we're all working towards and excited to share with you today. In a second. We're very excited to share this with you today. We're we're so excited that we're going to give a little more of a dramatic entry. We're good, we think? Okay. So the Mars Rover design team at Missouri S&T is very excited and very proud to present our 13th rover, Talos. Turn it up a little higher, probably for pointer. Back up a little bit. It doesn't like carpet too much, but it'll turn around. Yeah, just do one of those. No, you're good. Okay, and as Talos turns back to the crowd, we're going to transition here into a higher level overview of our rover systems, how all of these stations you see around are connected, and how they contribute to our ultimate success at competition. So to do that, I'm going to pass it off to our Chief Technical Officer, Remy.
Hello, everybody. Like Abby said, I'm Remy. I'm the Chief Technical Officer. I'm also the 2018 freshman that got to work with Jack and get to work with your sons and daughters on the team, friends and family. But thank you guys for being here. So today, I'm going to go over a technical overview of how our systems work, and for helping me in showing our systems, Dom and Morgan and some of our members are going to do some live demos, and we'll see how they go. So first, want to talk about our base station interface. So Morgan already kind of talked about how we control the rover, but over here at our command station, we have our base station where operators can use controllers for us to send commands to the rover and for the rover to send data back to us. Things like camera streams, GPS data, the battery power, stuff like that all gets reported to us from the base station. So Morgan is kind of overseeing the progress of this. And this year's base station has a complete rewrite of our GUI. So during this entire calendar year, or this academic year, we've been working to rewrite that and test our new base station to have the most capability that we can. Next, I want to talk about our signals on our rover. So the rover uses 3 different radio frequencies to communicate from these here signal stacks to the antennas on the rover. So this is how we get data from the rover and get commands sent to the rover. We also have many cameras on the rover for us to drive from. So this is an example camera view that we see as operators. And Dom is kind of waving in front of some of the cameras that are on rover. And you can see the live feed of Dom's arm over on the base station over there. But when we do operate the rover, it is fully remote. So we are not able to see the rover. We're at competition. We're in a U-Haul with our base station. We have 4 to 5 operators driving our systems, and we have to be able to accurately and precisely drive the rover using only these camera views. So it is very difficult. We have some latency in our cameras, and we also have some low quality cameras every once in a while, but that's the way that we actually drive the rover. Next, I want to talk about the core rover itself and the suspension and the capabilities that it has. So Dom, if you could actuate the suspension. This is the 10th or so iteration of our Mantis suspension. So this is a custom-built suspension that is designed to go over rocks, go up steep slopes, down 1 meter drops, and has given us a lot of success at competition. It's comprised of some composite linkages, the composite main body, and then a lot of aluminum components attaching those together. But the real advantage that this gives us over other teams and other competitors is the ability for those wheels to get so much vertical travel and for us to never get stuck at competition. A lot of other rover teams are building a lot smaller platforms, but we've stuck with this much larger one, and we can kind of avoid obstacles and ignore them as we drive over rocks and up steep inclines and those sorts of things. If you guys want to get the block. They're going to go ahead and put the rover on a block for us to get it off the ground and show some more capability of the suspension system itself. So each of the sides of the suspension are linked through a differential bar. So as you can see, as Dom actuates one side of the suspension, both sides actuate in an opposite manner. So this gives us stability. If we have a disturbance on one side of the rover, it gets transferred to the other side and helps us to keep our rover flat. Our rover is driven through some new propulsion units that have motors and gearboxes in them. If you could drive the wheels at a reasonably high speed. I believe this is only 50% of our power, but this allows us to go very, very fast. Even at like a 40% or 50% drive speed, our members cannot keep up with the rover while we're running. At 100%, it would just be blitzing down the field. It is honestly way too fast. We don't need to use that at competition, but it does help to have the overhead on speed and on power for us to get unlodged if we do get stuck. These wheels that we have on the rover are some plastic rubbery wheels for us to be able to drive inside. Normally we have carbon wheels that we use that have a little bit better grip on the Utah sand, and they're a lot more lightweight than this. Dom, if you want to lift the lid. On the rover, all of our core electronics are stored within the frame of the rover. So if you were looking at a top-down view of the rover, this is what you would see. This is where all of our custom PCBs are, our rover battery, all of the different sensors and electronics that go in the rover go into our custom composite frame. The frame itself is also a structural member, so it is not just a box for the electronics. It's where the arm hangs off of, the suspension attaches to, and it does act as a structural member for our suspension. Next, going to talk about the arm on the rover, so if we can get it back on the ground. The systems that go on the front of the rover, we refer to them as our auxiliary systems. So these are the ARM system, the science system, and the autonomy system. We have a sort of quick change auxiliary mounting system on the front of the rover that allows us to seamlessly and quickly change systems between tasks. And yeah, so we'll kind of show that off here in a bit, but now we're going to talk about the arm. So Chase is going to drive the arm around and show some of its capabilities. You can go for it. But yeah, so Dom's got a hammer to deliver it to the arm. But this arm is a new design for us. It's a 6-axis arm that does not have the ability to kind of roll like your shoulder does, but it gives us some additional control that we haven't had in previous years. One of the main sort of design decisions that we went for, or the main focus that we've had, is controllability of the arm and being able to accurately control the joints simultaneously. So like on your arm, if you want to go grab something, you obviously move all of the joints at the same time. It's quite easy, and we're trying to mimic that motion with this arm. If we had to move each joint one at a time, like move my elbow and then move my wrist and move my shoulder, we lose time on that, we lose precision. So very early in the year, at this point, we have inverse kinematics and closed loop control on the arm working, and yeah, just have the ability for us to drive those axes sort of seamlessly. On the end of the arm, we have a gripper that's used for all of the competition tasks, things like picking up weights, flipping switches, pushing buttons, that sort of stuff. And on the other side of the arm, the other side of the end effector, we have another button pusher that we use for typing. Typing on a keyboard is one of the main competition tasks of the equipment servicing mission, and so that's why we have the second end effector on the arm. That's not the gripper. At this point, Ethan and Dom are going to take the arm off of the system, so you can kind of keep your attention on them doing the NASCAR pit change, but I'll talk about the autonomy system now as well. So if Bailey and Sam can come up here with AR tags and things. So when the arm comes off the rover, we're able to swap on the autonomy head or swap on the science system. And so this is our autonomy head, and this is what we use for camera vision and for our ability to complete the autonomous task. So this requires us at competition to drive autonomously. This is where the rover is not controlled by us. There's no operators. We just tell the rover to go, and it on its own drives around the competition field. So it has to find GPS points. It has to find these AR tags that Sam's holding, and it has to find objects like water bottles and hammers and be able to stop within 1 or 2 meters of those waypoints for us to get points for the task. The autonomy head itself has a lot of cameras on it, and that's how we actually find these items. And so the software team has integrated those cameras with some sensors, things like ultrasonic sensors and GPS data for the rover to know where it's at and to make intelligent decisions while it's driving around the field. Next, going to talk about our science system. So now we have our science system on the rover, and the main point of the science system and the science task is for us to find some signs of life on Mars, or in our case, in Utah. So the science system is split into 2 main systems. The one on, I think, my left is the auger. So this is a soil acquisition system. This allows us to drill into the ground and acquire soil samples, and the competition requires us to then analyze that sample and also cache it, so store it on the rover for us to then take off, seal, and give to judges for them to do more analysis with. But that's the point of that auging system, is for us to drill into the ground at least 10 centimeters and for us to get soil and analyze it. The other gantry is an instruments gantry, so this has our scientific instruments on it. This primarily has a Raman spectrometer where we shoot laser light at the sample, and based on the wavelengths that the sample emits and absorbs, we can infer what molecules are in the sample, and from there kind of make a guess as to, was there life in the sample, is there active life, or is there dead life in the sample, or no life at all, sorry. And then finally, there's a microscope on the system as well, and this allows us to get a really close-up view of the soil, of rocks, and be able to make calls on what we see. Does it look like there's evidence of water, those sorts of things on the system. That task then, our scientists have to take all of the data we get at competition and make a presentation to the judges explaining to them our scientific rationale and the data that we collected on site, and then kind of present that to them and tell them what we found. The drone is what's next. I think Jesse is going to bring the drone. Accompanying the Rover is also a custom-built drone. The point of this addition is to, for one, look at the field for us. So this can hover in the air and give us a bird's eye view of what does the field look like. Where are the different objects and astronauts in the field, and where might there be a good path to take and maybe another worse path to take. This also, this year is acting as a signal relay for us. So the drone will have the capability for us to shoot signals directly to the drone, and then the drone to repeat those signals to the rover. And the capability that gives us is better signal quality and better out of line of sight signals. And so still working on drone development, getting like the first flight of the year, but have some development there on our signals. So those are all of our main rover systems. Like Abby said, I definitely want you guys to explore these systems a bit more. Come look at the rover. You can pick up the wheels and kind of play with it and look at how it functions, ask questions. But yeah, all of this development that we've done has happened in the last 6 to 8 months. That's really the incredible thing about this team, is that we do build a new rover every year. The team that won competition last year, in their video this year, they claimed that it's their 7th year of using the same rover. During that time, we've built 7 rovers. So being able to do that every year and work to grow our members and grow our systems has been really good to like work with everybody and see what we can do as a team. To give you guys some perspective as well on our systems, with all of the systems we've presented today, the first one that we had even mechanically standing was January 13th, was the arm. So before that point, we had some incremental progress in getting some parts manufactured, getting some parts designed, but at that point, we really didn't have any physical systems to work on, to test, and kind of work through. And so actually being able in the last 6 to 8 weeks to make all of this progress is quite crazy for us to get all this stuff to come together, to have the rover driving, for us to have all of our rover functionalities. We're in a really good spot leading up to competition, but please do ask us about the timelines, how we work, what we work on when, because I think that's kind of the most interesting part of the team in how we operate, when we operate, and kind of the intensity that we do it at. So yeah, all of the systems that we've presented today, we have now submitted a SAR package to URC. So this is our official competition submission for us to tell them, hey, we're ready to come out to Utah. We have all of our rover functionalities. And this is a scored submission in which we compete against other universities for them to allow us to even go compete in the desert. There's still a possibility that they look at what we've built and say, no, you're not good enough. There's 36 teams better than you. But we're still awaiting that decision. And we've never not made it to competition, fingers crossed. That announcement's coming up for us if we do get into competition, but want to show you guys here our SAR video. So this is a 5-minute video that we submit to competition. It's mostly technical content, so some of it's repeat of what I said and maybe a little bit more in depth, but should show the rover functioning and show all of the different functionalities that we do have.
The Mars Rover design team at Missouri S&T has been working to design, build, and test entirely new systems, optimized for performance in 2025 URC missions. We are proud to present our 13th rover, Talos.
Our base station software uses a complete rewrite of our custom GUI, written in the Blazor app framework to allow for multiple clients to communicate with Talos simultaneously. Our main base station system hosts a server which handles database management and displays core rover data, with additional clients used to display camera feeds and instrument data for use in controlling the auxiliary systems. This enables a more efficient workflow by improving usability and collaboration among operators. Upgraded telemetry between MRDT's base station and rover now simultaneously utilizes the 900 MHz, 2.4, and 5.8 GHz frequency bands. Our network selects optimal communication paths based on metrics like bandwidth, delay, and reliability, meaning high bandwidth applications like camera feeds will prioritize higher frequency channels.
Talos features a new iteration of our custom Manta suspension with a smaller profile and lighter overall design. A complete redesign of our propulsion units offers increased torque and electrical efficiency without any increase in weight. Talos remains stable while navigating tight paths, climbing steep inclines, and withstanding vertical drops. The structural composite frame houses the distributed architecture of the rover's electrical system, which accelerates troubleshooting and reduces failure severity. The health of our electrical system is monitored using individual cell voltage and current sensing of our custom 6S 8P battery. Camera gimbals allow operators extensive views of Talos and its surroundings. Paired with the new robotic arm, we can locate, carry, and deliver objects across various terrains. MRDT's custom drone now serves as a signal relay between our base station and rover during the delivery mission, significantly improving our out-of-line-of-sight signal reliability.
Our new robotic arm uses one horizontal linear axis and 5 rotational joints, providing the ease of control, strength, and range of motion necessary for fine manipulation. The arm is driven with DC gear motors and is equipped with absolute magnetic encoders, limit switches, and mechanical hard stops to achieve reliable position control. The arm features a robust under-actuated gripper used for lifting and manipulating objects, along with an additional end effector that uses a laser-aligned solenoid for precisely typing on a keyboard. Cameras on the arm provide operators with a view of the arm's position and its environment.
The control system of our arm has been a priority. A custom 3D simulation software was written to model the arm and its controls. This model is used for realistic visualization of the arm's movements in pursuit of inverse kinematics and PID control. Using inverse kinematics, the arm can easily be controlled in closed loop, allowing for predictable point-to-point movement, which is essential as we continue development of the arm's autonomous typing capabilities.
Our autonomy software has seen continued improvements. Differential GPS enables precise navigation, while a 290-degree field of view, achieved through a Z2i stereo camera and 2 Z minis, allow for AR tag detection via the Aruco library. A fast SAM model is used to detect objects and potential obstacles and store their absolute positions, while 2 ultrasonic sensors provide redundancy in preventing potential collisions. Meanwhile, USGS LiDAR data provides general path planning guidance, ensuring we navigate around large obstacles. An A-star algorithm then charts a safe path for Talos to follow. In search of objectives, Talos will enter up to 3 distinct search patterns to scan the surrounding area. An LED matrix and an indicator at base station indicate the rover's autonomous state, and signal when it reaches a GNSS point, AR tag, or detected object. To accelerate development, we built a custom simulator in Unreal Engine, incorporating accurate environments and realistic physics using a virtual model of our rover. Autonomous operations are tested in the simulator, and the resulting performance is used to improve real rover capability.
Our science system utilizes 2 single-axis Cartesian gantries with onboard cameras to document wide-angle and high-resolution pictures for the investigation of multiple sites, while locations and elevations are retrieved from our rover's differential GPS. The instrument gantry consists of a microscope for soil analysis and a custom-built Raman spectrometer. This instrument enables the identification of mineral samples, amino and nucleic acids, complex organic and biological structures, and organic solvents within a sample. The soil acquisition gantry includes an auger for collection and caching for later evaluation of subsurface soil. For analysis of the cache sample, a custom-built autofluorescence microscope is mounted for observing the presence of FAD and NAD, along with sensors to measure temperature and humidity at a depth of 10 centimeters below the site surface.
Our team is also committed to expanding our capabilities through the pursuit of R&D projects. The development of a custom-built offset Raman spectrometer for both surface and subsurface analysis, and a brushless robotic arm with a custom cycloidal actuator are examples of these innovative projects. Everything shown, with the exception of continued development on our drone and autonomy codebase, has been fabricated, integrated, and tested during the URC 2025 competition cycle. The Mars Rover design team thanks you for your consideration to compete in this year's University Rover Challenge.
A lot of nights that went into that, lots of rain, lots of mud, lots of snow. It was a lot of fun, but we got that video submitted. We're very proud of it. I hope you guys are too. But a little bit about what I'm going to go into. My name is Will Weidler. I'm the Chief Financial Officer for the Mars Rover design team. So I handle all the finances. I order the parts for the rover. I make sure that the leads are staying to their budgets that they set at the beginning of the year, making sure that we're in good standing with the design center, the university, and with URC at competition. So, as you've seen, our team's put together something pretty amazing. I'm very proud of our Rover Talos. All of that is brand new this year, and a lot of people have learned a lot from it. But building a rover and going to competition isn't free, as much as I wish it was. So, one thing, as a student-led and student-funded organization, we're responsible of going to sponsors, corporate donations to sponsor our team, to build the money to build something like this, and go to competition. One of the things that we do every year is crowdfunding. So we do reach out to our alumni network, our family and friends, in different departments on campus to support us to get us from here in Rolla, Missouri, all the way to Hanksville, Utah, which is a 2-day trip with all of our equipment, our rover, and about 20-some people. So I want to help, if we can go to the next slide. Actually, I clicked that, that's right. Here we go. So here's a little bit of details about this. Some of you might have received some pledge information about that, but we are live with our campaign now. So today, alongside with Rover Reveal, we are launching our crowdfunding campaign. It's going for about 10 days, and we are reaching a goal of $10,000, which has not been done before. It's a little bit eager goal, but I'm really certain that we can get there. If you want to see up here, there's a little bit of a breakdown about where your support goes. So gas, rental vans for getting us down there, housing for our team, food, and then different uniforms that we wear on competition there. So there's a lot that goes into competition. It's very expensive, and to make sure that we're doing our due diligence of getting everyone there safely and with the right money and food that we need to get there and do our competition very well, we crowdfund. It's also really good for our team to know that we have the support of our family and friends and alumni backing us. It inspires us to do our best at this competition, and knowing that we have people cheering us on from home, even if it's just from a donation like this, it really does help. So if you guys want to scan that QR code, you'll get taken to our crowdfunding page. That'll be up, like I said, for about 10 to 14 days from here. If you don't have your phone out now, can't scan it, no worries. You can go to go.mst.edu/Mars Rover crowdfunding. And don't worry now if you don't remember this later. We'll be sharing this on social media. Make sure to follow us on Instagram and Facebook at Missouri MRDT. We'll be sharing updates there with how crowdfunding is going. So, on behalf of the team, I do want to thank you guys for coming. We're nearing the end of our formal presentation of Rover Reveal. It really means a lot for us to come, for you all to come here from wherever you're coming from to Rolla, Missouri to see our rover. We're really passionate about this, and it means a lot to have your support. We also want to thank the Student Design Center down the street for always sponsoring us and supporting us everywhere we can go with this rover. Without them, we couldn't build this. We wouldn't have the place to build that, the rover like this, and really learn these different tasks that we need for going into our careers. Learning new skills like machining this carbon fiber, or forming the carbon fiber with epoxy, machining these parts, writing the software we do with the base station, and integrating it all together with such a collaborative environment. So we thank the Design Center for that. And our team advisors, our faculty advisors, without their support, we wouldn't have the knowledge, the foresight from their experience and careers to really help us guide us while we're going through this competition and different tasks about building this rover. So we thank them a lot as well. And yeah, now we're heading into a time to mingle. So just in a second here, we'll all be free. Leads will go to their different stations where you can ask specific questions about software, mechanical, electrical, and science, just around here. And also merch is available for purchase by the table right by the door or the wall here. The red table. Merch is available with cash only. We only do have cash, but we do have change. So if you have cash that we want to bring some stuff down into, that is perfectly fine as well. But yeah, thank you all for coming, and on behalf of the team, we're looking forward for a good year, and thank you for coming.
Slide is thank you. So we'll kind of hit the nail on the head, but yes, we are going to disperse again the rover and the base station system. We're putting the arm back on. They're going to stay up here. They're going to stay unpowered for a little bit because we want you guys to be able to come up and touch and no fingers pinched, no safety issues. So rover unpowered for a little bit, ask questions, touch the rover, see the inside. As kind of the mingling disperses, we can power it again, pick up random objects, maybe even drive outside, do some donuts, things of that nature.
And then we'll have those 5 stations out there as well that you guys were starting to look at, but we'll fire up our demonstrations and other things again. So please walk around, ask questions, and enjoy yourselves. And thank you all again for joining us for our Rover reveal. Thank you.
You can hear anything?
Oh no, that whole time it was
No.
muted?
No, that microphone's out of range.
Are we good now?
You'll have to talk into this microphone.
Cool. Microphone's back. Hopefully you
Did
guys
they
were
hear
able
the autonomy?
Yeah.
We can go back.
Hopefully you guys were able to hear some of that stuff. Do you want me to go back over all of it? I mean, we don't have to if you don't want to.
I guess so. You
Okay.
can go over it again.
Cool.
I don't know if they can.
Go ahead.
Yeah.
I'm stealing your thunder.
Oh shit.
Sorry if you guys couldn't hear that. Earlier what I said was this is one of our PR wheels. This is what we have on the Rover. This is what we tried making last year, but it was really easy to squish, which meant that it didn't really work for Rover Reveal. So we had to make six wheels in 5 days, which was not fun. Our wheels normally look like this, which you probably saw in the video. It is 6 layers of carbon fiber with steel toes bonded on the sides. That's because whenever we drive, this little bit right here, the carbon will crack instantly if we don't have these steel toes protecting it. With other things, it's designed like a mini bun cake for the purpose that in the desert, while you still want to wheel, you want to be able to use it like a boat propeller going through sand. Yeah.
Obviously, it's iterative.
Probably good.
Yeah, like each of the documents, the other one's had like a big old shaft coming out of the center.
And then what do we use the drone for?
Center of those wheels.
So we mainly use the drone for signal repeating and camera surveillance microphones. We use the drone for signal repeating and camera surveillance. We basically will fly the drone up, survey the area before we go to task, and then land it and have it repeat our signals to and from the other place. It's made very lightweight with carbon fiber tubes and fiberglass legs.
Yeah. No, we usually keep the old Rovers intact and don't use much of that.
All right. Cooper,
in general, right? When you're designing the
live stream.
We don't really do simulations. A lot of our things we
Explain
can
the
do
electronics.
Electricity goes in and they
There's
work.
a few times we
and
do
then
simulations.
We
but
have
that's
software
for
to help other
the
stuff.
really advanced stuff. Most of the stuff we do is simple
part
enough
of
that you
it.
can just calculate out.
This is
The math
last
isn't too
year's
bad.
power management system. So it's the electrical distribution from the battery, and then it also monitors the battery health as a BMS, battery management system, so it can look at the cells itself inside of the battery and like the health of that, so we can see the voltage levels of if it's dangerous or not, or we can tell when our battery's drained and we need to charge again. And we make all of our PCBs in-house, and we teach all of our members how to solder, both like hand soldering and reflow soldering, and we do our C++ programming with our teensy microcontrollers, which we have some at that table over there. We also have an ARM simulator that he's going to show.
I didn't really understand what that meant.
So-
and how you drive the arm, and he helped really explain it. I was wondering if you just pick a target and tell the arm to kind of get there, figure out which motor should do what, and take you there.
Yeah, and that's, you can either give it a, move in this direction, or you can say move to this point, and it is able to back convert what each individual joint needs to be to get there.
Oh, even with move in this direction, it's going to involve multiple joints.
Yeah.
And so even that has to work it out.
Yeah, because something like left and right's easy because there's just the x-axis on the front of the Rover, but you think of something like up-down, you have to move multiple joints. And so, instead of having to move each of those individually, you have the inverse command software here that's able to do the math and say, this is how each of those joints has to move.
Okay.
It's supposed to be the DVD logo. It's hard to see in the stream.
Not that I really understand all of it. I'm just absolutely blown away with not at all. I'm just trying to figure it out.
So,
and this is a motor that's being controlled by a PWM signal, and you can see that on the oscilloscope here.
PWM is pulse width oscillation, so we can send a pulse every periodic time. So we can tell it like the speed, so you can see this motor's like slowly speeding up and then slowing down.
And who's telling it to do that?
These guys.
Oh,
These are
okay.
microcontrollers.
Oh.
It's the brain that makes it run.
Oh,
And
okay.
We can send software to that, and then the software controls this chip.
Amazing.
That we've made. And then it powers it.
Does it also tell it what color to show on there?
Yeah.
It
So
does?
we actually made this last night.
Last night?
Yeah.
Yeah. It came over.
Wow. Very impressive. Very impressive.
There you go.
Not bad.
The live stream's here.
Oh, let's go.
Is the breaker still tripped?
No. Well, the breaker is tripped, but we used a different supply. It needs a little bit of grease, but yeah, it fully runs. You can do base station as well for the temperature and humidity reading.
See, that's what they dig up.
Close up of the electronic.
Yep.
Don't touch it.
No, you're good. You can touch anything. Wrong shit for touching. Yeah, so that's a sand sample from the location in Utah that we go to.
Oh, is that from last year?
I think so. So,
And what is that?
just this is from Utah. So that is a sample of this.
Oh,
So that's what you see on the
oh,
model.
that's what we see on the model?
Yes, exactly. Yeah. Yeah, these rocks aren't from Utah. Yeah, so we have
So what do you have to do during the science test?
We have to collect a soil sample from below 10 centimeters. That's what the auger gantry over here does. It'll go down to 10 centimeters, drill up dirt, and then collect it in a bag over there. Then we also have to identify samples and determine whether they have life or not. So for quick analysis, we use a microscope, which is usually mounted here, but is right over there for a demo.
That's the spectrometer.
Yeah, so that's the Raman.
We also use our Raman spectrometer to do more in-depth analysis of habitability and life. And that's what this box right here is. It's got a laser right here for excitation of the sample, and then it goes through an optical array in here and is read by a CCD right over there. You can't really see much of it because it all has to be light tight, but yeah, that's what our analysis suite is.
And who are you?
I'm Jesse, the Science Electrical lead. We have a couple of demos set up over there.
All right.
Oh yeah.
This is a model of the setup that we use to split the light that we get from our Raman spectrometer.
Okay.
So that's like the objective that collects the light. We shoot the laser at the sample and emits different spectra, so different wavelengths of light. This will split up all the wavelengths, so you can see it kind of comes in one single wavelength, and then it splits into each of its different things. It focuses them onto a camera, so this is kind of our sensor. So that's how we measure which wavelengths are at which intensities.
Okay, so you're kind of calibrating your detector.
Yeah.
And so that tells you then when you go and when you actually do the Raman sample. So this is like you're shooting invisible light and calibrating the detector. And then you're going to do the Raman spectra. And the Raman spectra is only going to give you like a couple of different lines. And now you're going to know where they overlap because of your calibration. Did I get that right?
Yeah, so we'll use like a special it makes like a really specific wavelength, and that's how we would calibrate it. So like you choose a known wavelength and you'll know if that wavelength falls there, and you might choose another one.
So what do these graphs tell you?
These graphs? These are, so this is the Raman peaks. You're headed out? So each of these peaks kind of corresponds to a vibration of different bonds in a molecule. So the molecule will vibrate, absorb some of the energy of the photon, and then emit a lower energy photon. So basically the energy difference from the laser light to the peak of light that we get tells you what bond in molecules you're looking at. So like carbon-carbon bonds have kind of their own vibration mode and special spectra. All the different bonds that you have in like an organic molecule will have their own signature peaks.
And so are you looking for one particular line or one particular type of bond, or are you looking at like a fingerprint of the entire Raman spectrum?
It's like a fingerprint. It's actually called, there's like a section of the energies that's called fingerprints.
Maybe a few minutes. At that. Like at most. 2 seconds to a couple minutes.
Welcome.
That's awesome. Nice to know. Hi, live stream.
Say hello.
Hello.
Welcome to the science system.
So what you got here?
Okay. Yeah, so right here we have the microscope, and we're looking at a sample from Utah. So, yeah. I guess. He's just been sitting out in spaces.
Very quickly.
Hopefully quickly, we know what to look for.
See, this is why microworkers, things like this.
Then again,
And I from down the cover of the dead body. Yeah, well, we came up with
You can use the auger on it. I'm showing the live stream the microscope. Let's see. What do you have here?
Okay, this is the autofluorescence microscope. So what we do is we use a pretty decently complicated system of mirrors and microscope objectives, so you can see it over there on the camera, on the computer, to bounce light around up through the LED board, through here, into the sample, and then the light will bounce right back into the camera where our sensor is. So right here is the microscope. So we're looking at a sample of sand from Utah at the site we can tell if there are any organic. So the microscope, we're looking for grain size and color and that kind of things, and we're looking for half signs of light.
So those are the. So that's glowing.
Analyze it, they go in.
So that's what you're looking for.
Yeah, that glow is what we're looking for. The sample right now is just full of glitter and dirt. We don't actually have the sample quite yet to test it, but it's this greenish kind of glow that really is what we're looking for, because calcite, which is often in the soil of Utah, fluoresces a bright red. So the green for the chemicals we want is diagnostic, and that it means that life has been there within the past couple hours.
Oh. So what is this?
Welcome live stream to the Raman spectrometer system. This Raman spectrometer is designed to detect signs of life on Earth via changes in laser wavelength that we shoot at it. A laser is mounted to this point right here, which is then sent into a mirror which reflects it down into the ground, which for our cases will be a flashlight for our demonstration I'll provide in a minute. This red part here seals the piece onto the ground to block any outside light from entering. As the light hits the ground and either excites the ground or gets excited by the ground. We can then send it back up through the mirror in a series of optics to filter out so that only the laser light makes it through a slit over at the front here if you want to move the camera just a little over. Yeah, that's the slit. So you send it right through here and it gets filtered out to be sent into the piece called the monochromator, which is everything from this part forward. This mirror here bounces into this diffraction grating. Diffraction grating will split the light into different wavelengths of light that we can then measure for data, which for us will be represented by different colors. This diffraction grating will then send it, if you'll move up a bit, from here over onto this mirror, which will then send it to what would normally be a sensor, but for our demonstration today, we've provided a nice whiteboard for you to witness what our spectrometer is capable of. You'll notice that only red through green are present in this Raman spectrometer because green is the color of our laser. This allows anything that's at a higher wavelength than our laser to be completely filtered out by the optics inside of the probe itself, allowing for our most accurate collection of data possible. Oh. Yes.
Cool. So you'd expect on an actual sample to see some light, some of it missing, because it gets absorbed by the ground. So the ground doesn't emit all the wavelengths.
Yes, so the ground itself will emit 3 types of scattering or excitation of the wavelength called Rayleigh, Stoke, and anti-Stoke. Anti-Stoke will be a decrease in wavelength, Rayleigh will be no change, and Stoke will be an increase. We are looking specifically for Stoke changes that allow our laser to be measured a specific change. If it sends back the exact same wavelength of the laser, it'll be reflected by the mirror and never make it into the monochromator system. This allows us to get only the data that we need and are concerned with into our filters.
There's actually something cool with this sensor. So, yeah.
Hi, Dad. I'm Tim. I'm Brady. Nice to meet you.
Here's the sim he was explaining earlier, but we didn't have audio, so yeah, this allows us to simulate autonomy beforehand, but we can also control it manually. We love running into trees.
So the reason that we have the simulator is so that we're able to simulate our autonomy before actually going out to competition. As in, this map is supposed to be a recreation of the grounds that we'll see at URC. And the main point is just for autonomous path planning, so we can test out, hey, is our rover able to successfully find all these tags, find all these objects, go to these waste points before we actually go into the desert, so that we're actually able to test out our capabilities. Because you never know, maybe it'll work in Rolla, but maybe not URC, which is why we try to simulate it here.
So what are these things?
So these are all of the AR tags, and what these are is they will be scattered across the map in Rolla. We also have other designs, as in we have 2 here, and then we have another one that is right here. And what we have to do is we have to go out into the desert and basically find them. We have to enter maybe a search pattern, or we are given a waypoint, and then we have to send our rover to go there. Either be like, hey, we have a waypoint here, go there, can we find it? Or we have to enter a search pattern and see there are all of these tags scattered on the desert. Are we able to detect that that tag is there, go to it, and signal that yes, we found a tag, we are here. And there are 3 of these scattered around, which is part of our autonomous mission. We also have objects that we have to find, but we don't have them represented here, unfortunately.
We'll see the hammer later. The arm has it. They're trying to get a multiplayer working. Yeah. So, but Bailey was explaining earlier. This is the auto box that goes on the rover. It has a stereoscopic camera, so it can see depth just with its vision by comparing the 2 perspectives, just like we see depth. And then inside, that would be connected to this Jetson, which is just a really beefy computer with a graphics card that can do all of that actually runs our autonomy software. And then there's also some ultrasonic sensors that are last resort in case we're about to collide with a big object, and they'll stop everything. Live stream.
On the Capitol Reef, which is the big fossilized reef.
All right, who are you? Okay. That's our arm mechanical lead. I've got the live stream. Does somebody want to talk about the arm to the live stream?
What? Oh, is that actually the live
This
stream?
is the live
I thought
stream.
You were screwing with me.
Yeah, no, this is
okay.
This is actually the live stream.
I hope. How many people are watching this?
Like 8.
Okay, well that's not too many people. I can deal with there being
D-thousand.
I'm gonna die now. What do we got? So it's an arm.
Yeah, there's 20 people currently watching it.
Oh dear.
Yeah. You got 5 rotational joints. 4, 5. And 1 slidey joint down there. Each joint is pretty well controlled. We've got absolute encoders on there. Between that and the motors, we can control exactly where it goes.
We're about to start moving. Do you want to kind of make sure there's a path to go somewhere?
Yeah.
I'm probably. You know what ice cream cone is on Jade? Oh, this. It's to like share the load over this tree because right now, like all the load would just be right there. This like kind of gives it a level, so it doesn't destroy the tree. It's supposed to be well enough. Like a second.
Antennas.
I also was very tempted.
So a few more things. I showed some of the electronics on the inside. This is an e-stop that we need so we can cut power to everything. The gearbox, when the audio was muted, we saw one of these gearboxes the cylindrical things. Those are the wheel motors. There's one of the lighting panels. We had a bunch of those displaying the DVD logo bouncing around, but it was a little hard to see. These are antennas, 900 megahertz, 2.4 gigahertz, 5.8 gigahertz, which feed into the rover to these radios, which connect to this network switch, which sends packets out over Ethernet to all of our circuit boards. And there's our battery. Yeah, this is the live stream. Say hi.
Hello.
There is someone watching it named La Pineapple. Is that?
That's Jacob.
Oh.
Hi, Jake.
Yep. Here's our arm board. All the inverse kinematics calculations are done on there, so that lets us set a target for the end to go to, and the arm will by itself figure out what rotations it needs to get there. So that's what Remy was saying when he meant. That's what Remy was saying when he said it's easier to move all of your joints at once like a real arm rather than one at a time. These fold out. So these are differential GPSs. So we have two. They fold out. Oh, we're getting a photo op. These are Antians. So there will be one of these at our base station and two of them on the rover. And based on the difference between them, we can account for the offset, like the error. So your phone only gets about 9 meters within a 9-meter radius of accuracy, but these can get down to the centimeter.
Specific instructions from Dominic. He wants the cameras angled forwards, whatever that means.
Okay. Dom wants the cameras angled forwards. So yeah, we can test all of the cameras. They're tied to servos. We can press these buttons. We can also control them with base station, but oh wait, where'd it go? Let's see, that's left drive. There. Left tilt is, let's reverse that. Left pan. And then left drive. Up. And then there you go. All forwards. So a few more things. Yeah, that's our gripper. This is a solenoid, so it strictly can itself out to type on a keyboard. And those are some lasers, so that intersect. When they intersect, we know we're the right distance from the key when their points intersect, because it'll be right there. Say hi, Remy.
What's going on? Is this a video?
That's the live stream.
They actually just
Live stream.
I'm pulling
So,
up the camera feed right now.
Oh, cameras. Yep. This is our base station.
Yep.
Shows. Are we connected to the rover?
We should be. Oh, did they turn it off? Okay.
Oh. Looks like they turned it off. Did they turn it off?
Should we? Do we need to rotate signals maybe? It's just like over there, right?
Yeah. Yeah, so this is our signal stack. 900 megahertz, 5.8 gigahertz, 2.4 gigahertz. Yeah. You can turn this over there. Point towards where they have the rover. Does this thing rotate?
rover might just be off.
Could be.
So this is the inside of base station.
Yep.
This is where we have the PC and the network switch, and a whole lot of Ethernet cables.
There's the other GPS.
Yeah.
That's the base station computer and the network switch for base station. So what's over here?
Right. So this is mini base station. This is essentially a second computer that hosts a second client on base station, because this year we've implemented what we call distributed architecture. So these two clients are actually completely synced up with each other. So if you look, I can start the autonomy timer from this client, and over there on main base station, you can see it started as well.
Oh, yeah.
Yeah. The same thing there. I can stop it, and you can see from over here, like base station stops, and I can start it again. You can see it starts over there, set it. That works with pretty much all systems.
So you can plug a phone, laptop, anything into the network switch there, and it will still pop up, right?
Yeah, because if you see here how we have it, we're using a web framework called Blazor. So our GUI is essentially just hosted in a website. So any device that can run a web browser can run a instance of base station on it. And this GUI is used to pretty much control every system on the rover. So you see over here.
What does GUI stand for?
Graphical User Interface.
Oh,
it's
okay.
also called a GUI sometimes.
So yeah.
Here we have it on ARM controls right now.
But we could open
science.
Yeah.
That's where we have our Raman graph readings.
Yeah, we saw this earlier.
Oh yeah, controls for our auger system and environmental data. Autonomy. This is where we have our state diagram. So once we start, here's our autonomy controls. Actually, we'll start here. We essentially add waypoints where we want our rover to autonomously drive to, and then we can start it and stop it. And this is how we view what driving state our autonomy program is in. Over here we have a map. We're not getting GPS data right now, so it's not loading, but you can see where we have all our waypoints set up. We also have nav here, which is basically just display of our latitude, longitude, heading, stuff like that.
Mm-hmm.
Just to double check where
So
we are.
what's all over here?
So this is our autonomy state diagram. So with the way autonomy works, we basically have a lot of different modes the rover can be in, and it will try to detect things or drive differently depending on what mode it's in. For example, idle is just when it's waiting for more commands. Navigating is when it's driving. When we want to search something for like an object or an AR tag, we'll enter search pattern. So we'll drive around and try to see if it can catch the AR tag or object we're trying to find. We also have extra states just in case of unideal conditions. For example, stuck here. If the rover isn't able to drive forward too long, it goes in the stuck state, and we'll try to reverse or other things like that to get out of it.
Yeah, we almost ran over one of the judges at competition because it got in stuck state and then drove back at max speed. Yeah, I think that's all the important ones. Oh yeah.
Networking, we have our ping tool here.
Yeah.
Right now, the rover doesn't seem to be on, so we're only getting our own local network. We have default. If you go to red, we have the drive controls. We can show those off. I suppose we have PMS, which just displays like the current of like the core system on the rover and the aux system, and also lets us manually reboot it or e-stop it or power cycle each specific part, like motors, core, or aux.
So e-stop just means turn all of the systems off. Suicide means disconnect it from the network too.
Yeah. Then here on tester, we have drive controls. So you can see here. Let me grab the controller. Actually, we have one over here.
Oh, there it is.
Yeah. We have drive controls.
We're not connected, so
Yeah,
it's
we're not
fine.
connected, so it's fine. So you see, as I'm moving the axes on this controller, we have these bars changing, like increasing. That's essentially how we're driving the motors. We also have a speed multiplier here. As Remy was talking about earlier during his speech, our wheels are extremely fast. So typically we're only driving them like at a maximum 20%. The speed you saw during the demonstration was 50, which is far too fast for the ground.
And also, sometimes the rover turns itself off because it thinks it's going too fast.
Yeah,
And
draws a lot of current.
Yeah, it draws too much current.
And we could also do things like control the gimbals from this component. Those are essentially parts on the rover that rotate around, and we have cameras mounted on them just so we can get a good view of our surroundings. Because during competition, we can't really watch the rover. During our demonstration, it was over here, but at competition, we're in our U-Haul, and all we have is base station and the cameras on there.
Yep. Why did they turn the rover off? Where'd they put
Probably
that?
because they're just moving.
Oh.
Good, are you?
Say hi to the live stream, Arno.
Hello, live stream.
He's retired. he was R&D, one of the R&D leads.
Come to see all the new features.
Oh yeah. One of the most requested features.
Oh, right.
Dark mode.
Dark mode.
Yeah, look at that.
Individual dark mode?
Yeah, individual dark mode.
Yeah, and of course you can also customize all of the layout, all of the components.
Does it help with the viewing angle?
Yeah, so a big feature we've been focusing on this year is a completely modular UI. So you see this might be hard to see on camera, but there's this little icon next to all the components. We can open it up. You see we have complete control over the position and scale of our components. So I just changed Y here from 0 to 30. You can see that component moves all the way down here.
And you can just change it to a completely different one if you wanted to, right?
Yeah. So we could also change it here. We see type. It's on PMS, but we can change it to really whatever we want. Like if we want a second waypoints for some reason, we can set it to that. If we want a camera display here, we can have that set up.
No cameras right now.
Yeah, no cameras right now since the rover's off, but that feature is also very useful because we can have lots of components that are centered around testing or troubleshooting, and they don't have to be visible all the time. So for example, here's our RoveCom tester. And typically when we're driving, we don't need this to be active, but if we're troubleshooting something, we can just switch it and bring it up, which is very nice. Let me just put this back.
Very cool. Let's see.
That is the base station.
I don't know, where should I take the live stream? I can show them Eli. They can see the merch. Oh yeah, the QR code. So this is our crowdfunding QR code. We'll send it out hopefully. We'll send a link later. But if you really want to scan it, yeah, that'll take you to the crowdfunding site. All donations are tax deductible. After you donate the university, because you do it through the university, it sends you. They'll email you the tax codes and stuff to get that information, tax receipt, and that is yeah. And there's more information on that Google form. Alrighty, yeah, we'll post the link to that hopefully. Hi, Aster. This is the live stream. Say hello.
Hello.
Yeah. You have some cool merch to show off.
Absolutely. Sorry, I'm losing my voice. We have our gray shirts, which you will see others out there that are not in this polo. We have our flight tags.
Very cool.
Sticky wallets for your phone. Quite a few patches. Our 10th anniversary shirt.
Oh.
With the progression of our rovers through the years. And our Hyperion shirt.
So that was last year's, yeah.
Yep.
Yeah, we've come a long ways. We've made a few more since then.
Yep.
Cool.
You have a wonderful opportunity to get your picture.
All right. I think that's all. Oh, they got is that multiplayer autonomy?
You actually go through it.
Is that multiplayer autonomy? Oh. Yeah, this is the live stream.
Let's go.
Say hi, Jace. Yeah. Carp. This is what our rover's made of. That's what it looks like before. We also make these tubes. Where we like wind this material, these fibers around an aluminum tube, and then covered it in epoxy and let it harden and bake it.
All the red is one.
Yeah, that's what Ethan was explaining earlier, but he was muted. So you had to do the live stream, Josie.
Yes, that's right.
Okay, I think that's everyone. All right. Well, I think that's all the exhibits. I guess that's all the exhibits for now. I guess do we have like any questions that anyone had? Or is there anything that I kind of glossed over that you'd like to see closer?